Hi everyone, welcome back. We shall now move on to the problems regarding kinetics of rigid bodies. Now before I directly go to the problems, I think it is better if you do some of the problems that is related to finding the mass moment of inertia. Okay, so mass moment of inertia. Now we had studied that the mass moment of inertia I can be given as integral r square dm, okay, where r represents the distance of that elemental mass dm from axis considered. So if I have a rigid body like this, okay, and you have an axis like this, and you consider a small elemental mass dm, okay, which is at a distance of r from this axis. So as such, the mass moment of inertia with respect to that axis is given by this equation. This corresponding integral is a volume integral. Okay, so in some textbooks, instead of a single integral, it is given as three different integrals, which indicates the corresponding integration with respect to the three coordinate directions x, y, and z. So whether you put one integral or whether you put three integrals, uh, the concept is the same. So as such, you may write I also like this format. Both indicate same thing. Now here dm indicates the mass of the differential element. Now if the entire rigid body here is having a constant density, okay, so as such I can replace dm as r square into rho into dv, where rho represents the density of the rigid body. So here rho represents the density of the rigid body. Remember one thing in mind, this equation is valid only for a rigid body with constant density. Okay. Now sometimes what happens is that we'll have to deal with what we call rigid bodies that are very thin, like plate-like objects. So for thin plate-like objects, okay, in this case we can represent dv as t into dA, where t represents the thickness of the plate, okay, where t represents thickness of the plate. So as such, the corresponding mass moment of inertia I can also be given as integral. Now here I'll put only two integral. As such, since I will not be integrating with respect to the other direction, I will ignore it. Okay, the small changes as such I will ignore it. So as such I can write this equation as I equals r square rho into t into dA. Okay, so where rho t indicates the mass per unit area. This is the corresponding mass moment of inertia. So if you are expressing in terms of the three directions, I will usually write it as I x x, I y y, I z z. Now in some textbooks, in order to differentiate between area moment of inertia and mass moment of inertia, okay, the mass moment of inertia is sometimes given with a suffix m, okay, sometimes given with a suffix m, okay, to distinguish between area moment of inertia and mass moment of inertia. We must have already discussed regarding area moment in the last semester when you had dealt with statics. Now besides this, you also have got product of inertia. The product of inertia that is given as I xy, which is equal to I yx, which is equal to integral xy dm. Sometimes this is also given as integral xy into dm. Now if rho is constant, then I can represent this as similarly I can get I yz, that is equal to I zy, that is equal to similarly I can also get I zx, that is equal to I xz, that is equal to volume integral zx into rho dv. So as such, I can express the products of inertia also in terms of differential volume. Here remember one thing is that the entire rigid body is having a constant density. Now remember one thing, as such, when I have value of I is equal to the volume integral r square rho dv, this corresponding dv as such is the elemental volume. So this elemental volume can be expressed either in terms of the Cartesian coordinates or any other coordinate system that is suitable for the question. So as such, dv as such can be sometimes dx into dy into dz. If you are using xyz coordinate system, so dv will be equal to dx into dy into dz. Okay, or else we may choose some other coordinate systems depending upon the convenience of the question. Okay, so it is very important that you choose a proper convenient system while solving the problems. Now I think this is sufficient for solving some of the problems regarding the mass moment of inertia. So let us go to the first problem. Find the mass moment of inertia Ixx for a very thin plate forming a quarter sector of a circle. The plate weighs 0.4 Newton. What is the second moment of inertia about the x-axis? What is the product of inertia? So as such, it is required to find the second moment of inertia of area as well as the mass moment of inertia and also the product of inertia as such. So we have to find here Ixx of A, that is the area moment of inertia, then Ixy of A, similarly Ixx, the mass moment of inertia, as well as the product of inertia. Now let us start here. Now you see this is a quarter of circle here, okay, having a radius of 100 mm. So assume I have a small element here. I'll show it to you in the next figure. You have the y-axis and the x-axis. This is the sector of the circle. So the first step is to find the area moment of inertia with respect to the x-axis. Since in this question it is also asked to find the area moment. So Ixxa, okay, the area moment of inertia which you had studied in your previous semester. So it can be given as double integral y square into dA. This is the corresponding equation here. Okay. Now since this is a question involving a circular area, you can express dA in terms of r theta coordinate rather than the xy coordinate here. So as such, suppose I have a small elemental area that is at a distance of r from the corresponding origin O. Okay, so here is this area, this is the length r, and along this length you have a differential length dr. Okay, so if this is angle theta, then this small corresponding angle will be equal to d theta. Now the angle d theta is very small, this corresponding length, okay, which is almost equal to this length because dr is very small, so that length will be equal to r d theta. Okay, now from the x-axis, say it is this corresponding elemental area, it is at a distance y. Okay, that is shown here. Okay, so as such, area moment of inertia as integral y square. You see this corresponding length is y, which I can represent in terms of r. Okay, so this will be r sine theta the whole square into dA. Now dA, it will be r d theta, that is this corresponding length. I take this as almost as a rectangle part, so r d theta into dr. Okay, so this is the corresponding dA part. Okay, so here remember one thing, I had expressed dA in terms of r and theta instead of the x and y coordinates. Okay, now solving this, I would get double integral r cube sine square theta into d theta into dr. Now here I'll put the limits of this, so let me just give it a small space here. Okay, so first my corresponding integration is with respect to theta, so theta will vary from 0 to the angle pi by 2. Okay, and the next is integration with respect to the r, so as such r will vary from 0 to radius that is given to you 100. So this will give me now 0 to 100, 0 to pi by 2, r cube into, now sine square theta, it is better if you express sine square theta in terms of cos theta. So sine square theta, as you know, can be expressed as half minus cos 2 theta by 2. Okay, whole multiplied by d theta into dr, which will be equal to 0 to 100. Now I shall integrate this corresponding term with respect to theta, so r cube will remain as it is, and half will be theta by 2 minus cos 2 theta. If I integrate it, I will get sine 2 theta divided by 2. So 2 into 2 will give me 4. Now this corresponding value will vary from pi by 2 to 0 into dr. Okay, so this will give me 0 to 100 r cube into, if I solve this term from pi by 2 to 0, I will get pi divided by 4 into dr. Now integrating with respect to r, I will get r raised to 4 by 4 from 0 to 100 into pi by 4, which will give me an answer 1.963 into 10 raised to 7 millimeter raised to 4. So here I had found the area moment of inertia. Okay, remember one thing, this area moment, okay, not mass moment of inertia. So as such, I am calculating area moment of inertia. So Ixx with respect to A. Next, I will find out Ixy. Okay, that is also I am finding the area moment. Now Ixy, as you know, I can give it as double integral x into y into dA is equal to x. If you go to the previous this one, this is the distance x. Okay, so this will be r cos theta. So this will be r cos theta into y, that is r sin theta into dA. Now here dA as such I can represent in terms of r and theta as r d theta into dr. Okay, so my integration will vary from 0 to 100 for r and 0 to pi by 2 for theta. R cube cos theta sin theta d theta into dr. Now cos theta sin theta as such I will express in terms of sin 2 theta. So this will give me r cube into sin 2 theta whole divided by 2 into d theta into dr. So this 0 to 100. Integrating with respect to theta, I would get r cube into sin 2 theta. I will get minus cos 2 theta divided by 2 into 2, which will give me 4. Okay, varying from theta equals 0 to pi by 2 into dr. So if I substitute this 0 to 100, r cube into this will give me minus 1 by 4 into minus 1 cos pi minus cos 0. So minus 1 into dr. So as such, if I integrate with respect to dr, I will get r raised to 4 by 4, varying from 0 to 100 multiplied by 2 by 4. Finally, this will give me 1.25 into 10 raised to 7 millimeter raised to 4. So here I find out the area moment of inertia. Now next we go to mass moment of inertia. Now Ixx, to distinguish, I will write it as m here, is equal to, now you have already found out the area moment of inertia. So in order to convert it into the mass moment of inertia, simply multiplied by density as well as thickness. So this will be equal to rho into T multiplied by Ixx into A. Now rho T, as I told you, it is mass per unit area. Now in the question it is given as the corresponding plate weighs 0.4 Newton. Okay, so as such, so this will be equal to 0.4. Now this is the corresponding weight. So in order to convert it to mass, 0.4 divided by 9.81. That divided by the total area. The total area, it is pi divided by 4 into 100 square. Since it is quarter of a circle, pi by 4 into 100 square. So if I solve this, I would get 5.19 into 10 raised to minus 6 kilogram per millimeter square. Okay, so as such, Ixx m will be equal to 5.19 into 10 raised to minus 6 multiplied by the value which I already obtained, 1.963 into 10 raised to 7, which will give me 101.88 kilogram millimeter square. Similarly, IXY, the product of inertia, will give me 5.19 into 10 raised to minus 6 multiplied by 1.25 into 10 raised to 7, which will give me 64.9 kilogram millimeter square. Okay, so as such we had find out the area moment of inertia as well as the moment of inertia with respect to xx and xy respectively. Now next question. Find the second moment of inertia about the y-axis for the front surface of a very thin plate. If the weight of the plate is 0.02 Newton per mm square, find the second moments of mass about the xy axis. What is the mass product of inertia IXY? So here corresponding curve is given to you. The equation of the curve is y equals 3x square. This is a very thin plate. It is having a weight of 0.02 Newton per mm square. So in this question we have to find out IXX, IYY as well as IXY. The mass moment of inertia with respect to the x-axis, the y-axis and xy axis. Now in this corresponding figure here, you see it is better if you express dA in terms of the x and y coordinates. So as such, if I have a small area dA here, okay, whose length along this will be dx and this will be dy. Okay, so this is the corresponding area. So as such, I can find the distance along, say it is x from the y-axis and y from the x-axis. So as such, first we will find out IXX. IXX, the moment of inertia with respect to x-axis, I can write it as double integral y square into rho into t into dA. Okay, so which this rho t can be brought outside. So rho into t double integral y square into dA, as such I can represent as dx dy. Okay, now this will be equal to rho into t double integral now this we can write the limits. Here x varies from 0 to 5 and y varies from 0 to 3x square. You see in this question here, the y will vary from 0 to till this equation of this line, and that value it is 3x square. So as such, this will be equal to, the integral will vary from 0 to 3x square. So y square into dx into dy. Now rho t into 0 to 5 integrating with respect to dy, this will give me y cube by 3 varying from 0 to 3x square into dx. Okay, so rho into t 0 to 5. If you substitute y equals 3x square here, you would get 9x raised to 6 into dx. Okay, so this is equal to rho t into, now this will be equal to 9x raised to 7 divided by 7 varying from 0 to 5. So as such, here rho t, okay, rho t, as I told you, it is mass per unit area. Now in the question it is directly given that if the weight of the plate, it is 0.02 Newton per mm square. Okay, so it is, so in order to convert it into mass per unit area, I will divide the value with 9.81. So this is equal to 0.2 divided by 9.81 kilogram per millimeter square. Okay, the unit here it is millimeter, so millimeter square. So this will give me 2.04 into 10 raised to minus 3 kilogram per millimeter square. So this will be 2.04 into 10 raised to minus 3 multiplied by, if you solve this, you would get 1.005 into 10 raised to 5. So if you multiply this, 204.91 kilogram millimeter square. Okay, so this is Ixx, the mass moment of inertia with respect to the x-axis. Now I'll find the mass moment of inertia with respect to the y-axis. So this will be directly equal to integral 0 to 5 integral 0 to 3x square into rho t into dx into dy is equal to rho t. I'll bring it outside. 0 to 5. Now x square as such, if I integrate it with y, I'll get x square into y. Okay, I'm integrating with respect to dy, so as such I'll get x square into y, value varying from 0 to 3x square into dx, which is equal to rho into t integral 0 to 5. If you substitute y equals 3x square, you will get 3x raised to 4 into dx is equal to rho into t. If you integrate with respect to dx, you would get 3x raised to 5 by 5, varying from 0 to 5. This is equal to, now rho t we had already obtained it earlier, that is equal to 2.04 into 10 raised to minus 3 multiplied by, if you solve this, 3x raised to 5 by 5, from 0 to 5 you will get 1875. Solving this, you will get 3.825 kilogram millimeter square. Okay, similarly the product of inertia will be equal to xy into rho t into dA. 0 to 5, 0 to 3x square, I think I'll write rho t here, multiplied by xy into dx into dy, which is equal to rho t into 0 to 5. If I integrate with respect to y, I'll get xy square by 2. Which is equal to rho into t integral 0 to 5. If I substitute y equals 3x square, I would get 9x raised to 5 divided by 2 into dx is equal to rho into t. Integrating with respect to dx, I would get 9x raised to 6 by 2 into 6, 12, varying from 0 to 5. Now rho t we have already got it as 2.04 into 10 raised to minus 3 multiplied by, if you saw this, you will get 1.172 into 10 raised to 4. So multiplying this both, you will get 23.906 kilogram millimeter square. So as such, I had find out Ixx, Iyy and Ixy. Now moving on to the next question. A body of revolution is shown. The radial distance r of the boundary from the x-axis is given as r equals 0.2 x square meter. What is the Ixx for a uniform density of 1600 kilogram per meter cube? So in this question, the density is given to you. Rho equals 1600 kilogram per meter cube. In order to find Ixx, the equation would be Ixx. I'm finding the mass moment of inertia, that is equal to the volume integral r square into rho into dv. Okay. Now here r is the distance of the boundary from the x-axis. So let me show you a figure here. Okay, I'll cut a section somewhere here. If I cut a section, if I have a section like this, okay, as such, if I draw that section here, you have the x-axis that is going like this, and then you have the y-axis and the z-axis. Okay, now in this corresponding question, instead of representing dv in terms of dx, dy and dz, we will be using, so as such, consider I have a small elemental area dA here. Okay, then you know, as we have studied earlier, this will be dr r dr, this distance will be r d theta. Okay, so dv I can represent as r d theta into dr, that is dA multiplied by the corresponding distance along the x direction, that is dx. Okay, so this is how we shall be representing as dv. Okay, so substituting it here, I will get r square into rho will remain as it is, dv will be r d theta dr into dx. I'll drop it here, Okay, so this is dv here. Now in order to know the limits, so I think first we'll integrate it with respect to x-axis, so it will vary from 0 to 1. Then I'll integrate it with respect to the theta angle, so it will vary from 0 to 2 pi. And the third one, I'll vary it with respect to r value, so that will be from 0 to 0.2 x square, rho cube into rho into r cube into rho into d theta dr dx. Now I'll bring the rho outside. Now I'll first integrate with respect to r. So as such, 0 to integral 0 to 1, integral 0 to 2 pi r raised to 4 divided by 4. The value ranges from 0 to 0.2 x square d theta into dx. Now this will be equal to rho 0 to 1, 0 to 2 pi, r raised to 4 will substitute 0.2 x raised to 4, so as such you will get 0.2 raised to 4 into x raised to 8 whole divided by 4. into d theta into dx. Next we integrate with respect to theta. So rho into 0 to 1. So 0.2 raised to 4 x raised to 8 by 4 into theta, where the value of theta ranges from 0 to 2 pi, okay, into dx. Okay. Now I shall integrate with respect to dx. So I will get rho into 2 pi into 0.2 raised to 4 x raised to 9 whole divided by 4 nines are 36. The value varies from 0 to 1. Okay. Now rho as such is given to you directly. Rho equals 1600 kilogram per meter cube. So 1600 multiplied by if you substitute the remaining of these values, you would get 2.79 into 10 raised to minus 4. So the answer will become 0.447 kilogram meter square. Now we shall move on to the next topic. So far you had been integrating with respect to dm or dA in order to obtain the moment of inertia. But in case you are given a problem which consists of a combination of standard shapes, in that case it is easier if you learn the equations for moment of inertia for standard solids. Okay, so as such it will be easier for you to directly use that corresponding equations to get the moment of inertia. Now here I had shown you a few solids in which the moment of inertia is given to you depending upon the axis chosen. Now on the leftmost side you see you have a hoop of a cylinder. Okay, you have a hoop of cylinder and the moment of inertia with respect to an axis that passes through the center of that hoop. In that case the value is I equals mr square. Then the same hoop as such, but instead of the central axis we are having the corresponding axis that passes through the diameter. Okay, so as such in this case the corresponding value of moment of inertia becomes mr square by 2. Here we have a thin cylindrical rod, and if you want to find the moment of inertia with respect to the axis that passes through the center and perpendicular to its length, then in that case the moment of inertia is ml square by 12. Similarly, the moment of inertia with respect to an axis that passes through the end of a thin rod. Remember one point here, it is a thin rod here. Okay, thin rod. In that case, the corresponding equation becomes ml square by 3. Now, in case of a solid cylinder or it can be a disc, if you want to find the moment of inertia with respect to the axis that passes through the center here as such, then the corresponding moment of inertia is mr square by 2 for a thick solid cylinder. Now for the same case, in case you are finding the moment of inertia with respect to the central diameter, okay, in that case the corresponding equation is mr square by 4 plus ml square by 12. So you have to remember one thing, depending upon the axis involved, these equations have been given to you, so don't get mixed up. One more thing, I'm not going to the derivation for finding the moment of inertia of each of these solid sections. Okay, I'll give some of these as homework as DHA. Now besides this, we also have the corresponding moment of inertia of a solid sphere. Okay, of a solid sphere, it is given as I equals to mr square divided by 5 with respect to a point that is passing through the diameter. And the moment of inertia for a thin spherical shell. Okay, this thin as such is very important. As such, the moment of inertia I equals to mr square divided by 3. And then you have the moment of inertia of an annular cylinder, okay, consists of an outer diameter r2 and an inner diameter r1. So in that case, the moment of inertia I is given as m by 2 r1 square plus r2 square. Similarly, moment of inertia of a solid slab here, okay, having one length a here and the other length b here. So as such, if this corresponding axis passes perpendicular to these two lengths, then the moment of inertia I is given as m into a square plus b square divided by 12. So it is important that you study these corresponding equations by heart so that you can apply them to solve problems. Now there is one more thing which I would like to discuss, that is with regards to the principal axis. Now I had already told you earlier that for a general three-dimensional rigid body, at a point there will be three principal axes, okay. These axes are perpendicular to each other. When I find the moment of inertia with respect to a set of coordinate axes, that corresponding axis may not be the principal axis. A principal axis is the axis oriented in such a way that the products of inertia is 0. That is ixy, iyz and izx. These values are 0. In that case, that corresponding set of axes is called the principal axis at a point. Now, when you have a set of principal axes, in that the moment of inertia in one of these axes will have a maximum value, okay. In another axis it will have a minimum value, and then a third axis the moment of inertia will be somewhere in between these two. Okay, now as such, identifying the principal axis is not easy, okay. In case of symmetrical bodies, okay, you may be able to identify the principal axis, but for a general three-dimensional body it may not be very easy to identify the principal axis. How do we identify the principal axis for a body that has some symmetry? Okay, now if there are two planes of symmetry, okay, if there are two planes of symmetry, with respect to a point, then the axis which forms the two planes of symmetry will be the principal axis. Now, if there is only one plane of symmetry, in that case, with respect to a point, in that case, the products of inertia between the axis normal to the plane of symmetry and any axis in the plane must be 0. So if you have a plane of symmetry and you have an axis that is perpendicular to that plane of symmetry and the corresponding axis that lies on this plane here, okay, this corresponding product of inertia of these two axes will be 0. For example, if this is say x axis and this is y axis, in that case ixy will be equal to 0. We may be able to say which product of inertia is 0, okay. So to identify, to get a better understanding of this concept, we shall look into the next question here. Identify by inspection any of the principal axes of inertia at points A, B and C. The density of the material is uniform. Now coming to the first figure here, First, let me take the point A. Okay, so at point A, as such, I can draw say 3 axis. X axis that passes like this. Okay, this is my y axis, and this is my z axis. Now, at this corresponding section, there are two different planes of symmetry. Okay, one is the xy plane. Okay, xy plane is a plane of symmetry. Okay, similarly, the xz plane here. Xz plane here is a plane of symmetry. Remember one thing, it depends upon how you are orienting this axis. Okay, so as such, if I take my xyz in this fashion, okay, I have a plane of symmetry along the plane xy, and I have a symmetry along the xz plane. Okay, so this is for the point A. I'll write it here, point A. Okay, so from this I can get that x, y and z are the principal axis. If I have two principal planes as such, and then I can finally write it directly like this. Okay, now coming to point B, let me draw the corresponding axis. Okay, you have here x dash, y dash and z dash. Now, let me write here plane of symmetry. Now, in this corresponding point B, there is only one plane of symmetry. So, x dash, y dash is the plane of symmetry. In such a case, you see, this is the x dash, y dash plane. Okay, and this z dash axis is normal to x dash, y dash. Okay, so the product of inertia between the axis that is normal to the plane of symmetry and any one of these axes that is lying in the plane, that will be equal to 0. So as such, I can write I z dash x dash will be equal to 0, as well as I z dash y dash will be equal to 0. Okay, as such, the z axis, okay, the z axis will be a principal axis. The z axis will be a principal axis. The other two axes, the other two principal axis, it may not be x dash and y dash, it may be some other axis. So that we'll have to find it out. Okay, now coming to the next figure. Now consider point A. So consider this is the x axis, this is the y axis, and this is the z axis at point A. Now if you look at this, there are two planes of symmetry. Okay, there are two planes of symmetry at point A. One plane of symmetry is xz, the other plane of symmetry, it is xy. So in that case, x, y and z are the principal axis. Now coming to point B. So in point B, assume, say I call it x1, y1, x1, y1 and z1. Okay, now in this case there is only one plane of symmetry. Okay, that plane is x dash, x1, z1. So let me write it here. Okay, x1, z1 is a plane of symmetry. So the corresponding axis that is normal to that plane of symmetry is y1. Okay, the y1 axis is perpendicular to the plane of symmetry. So as such, my product of inertia I x1 y1 will be equal to 0 and I z1 y1 will be equal to 0. Okay, so in this case y1 will be the principal axis. Now coming to the point C. Okay, say this is x2, this is y2 and this is z2. Okay, now let me write it here, point C. Now in point C there is only one plane of symmetry and that plane it is x2 y2. Okay, so x2 y2 is the plane of symmetry and z2 is the axis that is perpendicular to the plane of symmetry. So I z2 x2 as well as I z2 y2 will be equal to 0, or in other words z2 is one of the principal axis. Okay, so as such you should be able to identify the principal axis based on the symmetry of the solid. Now going on to the next question. A block having a uniform density of 5 grams per centimeter cube has a hole of diameter 40 mm cut out. What are the principal moments of inertia at a point A at the centroid of the right face of the block? So you have a block here out of which a cylindrical part has been removed. Okay, now it is required to find the moments of inertia about the point A. I hope you remember the equations of the mass moment of inertia for standard solids, which we shall be using right now. So if you remember it rightly, if you recall it, okay, for a solid block, the moment of inertia, okay, about an axis that is passing through the center of that solid, okay, it is given as m into a square plus b square divided by 12, where a and b represents the corresponding widths of the block perpendicular to the axis. Now for a cylinder, okay, for a cylinder I can find the moments of inertia with respect to the cylinder axis, the cylindrical axis, which is equal to mr square by 2, as well as the central diameter axis. I is equal to mr square by 4 plus ml square divided by 12. Okay, let me show you those here. Okay, so here mr square by 2 and mr square by 4 plus ml square by 12. This is for the corresponding solid cylinder, and in case of a solid block here, this is the corresponding equation. Now for solving such problems, okay, what we do is that we find the moments of inertia with respect to the axis that we already know. Okay, so as such we know the equation for the solid block with respect to axis that is passing through the center of that block. Okay, and then by using the parallel axis theorem, we can find the moment of inertia with respect to an axis that is parallel to it. Okay, so this is how you solve such problems. So first, let me fix the corresponding axis at point A. So say this is my x-axis, this is my y-axis, and this is my z-axis. I will fix my axis in this way. Okay. Now I shall reproduce this figure here once again. So as such, I shall take the moment of inertia of this entire solid block and then minus the moment of inertia of this cylindrical section here that is removed from this block here. So I need to know the mass of the entire block here as well as the mass of this cylinder here. Okay, so mass of the block, solid slab, mass of a solid slab, say I name it as M1, that will be equal to, okay, now I am expressing all these dimensions in centimeters. So as such, mass will be equal to the corresponding volume, that is 10 into 8 into 9 multiplied by the density. Now the density is given to you in the question as 5 gram per centimeter cube. The purpose of converting these dimensions in centimeter was to multiply it directly. So as such, you can multiply it with the density here. So multiplying it by 5 here, this become multiplied by 5, 3600 grams. Okay, then mass of the cylindrical hole. Now as such, the cylindrical part has been removed, but I would find the corresponding mass of that volume if it was present there. So as such, this would be equal to the volume of the cylindrical mass as such can be given as pi into, now the radius as such in this question, the diameter has been given to you 40 mm, so the radius will be 20 mm or 2 centimeter. So as such, pi into 2 square into 9 multiplied by the density 5. So as such, this would give me 565.487 grams. Now next, I find the mass moment of inertia with respect to the x-axis axis. Okay, so you have this axis that is passing through this point here. Okay, to the point A that goes like this. So first, I can obtain the corresponding moment of inertia of the solid slab here as well as cylindrical removed portion with respect to this point, that is the center of this corresponding block here. Okay, and then I can use the parallel axis theorem to obtain the moment of inertia with respect to this axis here, since this axis will be parallel to this. Okay, so what is the moment of inertia of this block with respect to this axis? Okay, that will be equal to m by 12, that is 3600 gram. The total mass is 3600 gram divided by 12 into a square plus b square, the corresponding lengths that is perpendicular to that axis. So that would be this 10 centimeter or 100 mm as well as 9 centimeter. Okay, this length as well as this length here. So into 10 square plus 9 square. Now this is the moment of inertia with respect to this axis. Now to transfer it to this corresponding axis, I'll have to use the parallax theorem. So you know the parallax theorem, plus the corresponding mass multiplied by the square of the distance between these two. Okay, so it will be half of this 10 centimeter or 100 mm. So this multiplied by phi square. Okay, so this is the corresponding moment of inertia of this solid block here with respect to this axis here. Now the cylindrical portion has been removed, so that portion I'll have to subtract it. So I'll write here minus. Okay, now since this corresponding cylindrical portion, I will consider it to be a solid cylinder rather than a thin cylinder. So as such, for a solid cylinder, the equation, as you remember it properly, it is the mass 565.487 into the corresponding radius square divided by 4 plus the mass 565.487 multiplied by the length square. The length square is this corresponding distance, that is 9 square. So 9 square divided by 12. Okay. Now this is with respect to this axis. Now this I'll have to use parallel axis theorem in order to shift this to this axis. So that will be equal to plus the total mass 565.487 multiplied by the distance between them, that is phi square. Okay. So if you solve this, you would get 144,300 minus, this is due to the solid slab, minus 18519.7. This is due to the removed cylindrical portion. So as such, this would give me 125,780.3 gram centimeter square. So this is the mass moment of inertia of this corresponding solid with respect to the x-axis. Okay. Similarly, you can find out the mass moment of inertia with respect to the y-axis. Iyy, that is equal to slab. Now first I find the moment of inertia due to the solid slab. Okay. Now moment of inertia due to the solid slab here. Okay. With respect to an axis that passes through the center of this point here. This axis will be the same as this axis. Okay, it will be passing. This is one single axis that passes through this point here. Okay, so this corresponding value will be equal to the mass divided by 12 into, now the sum of the squares of the edges that is perpendicular to this axis. Okay, that will be equal to 9 square, this as well as this corresponding edges. So 9 square plus 8 square. So 9 square plus 8 square. I don't need to use the parallel axis theorem here. Okay, since this axis is the same axis, that is y-axis. Okay, so this, now minus. Now due to the cylinder here, it is also the same axis that passes here. Okay, so as such, there is no need for using the parallel axis theorem. So this would be equal to 565.487 into the corresponding radius square divided by 4 plus 565.487 into the length square divided by 12. Okay, so if I solve this, I would get 43500 minus 4382.52, which would be equal to 39117.48 gram into centimeter square. Okay, you can either write it as GM also. The earlier slide also you can write it as GM, gram centimeter square. So this is IYY. Similarly, I can find IZZ with respect to the Z axis that passes through this point here. Now first to the solid slab here, this will be equal to 3600 divided by 12 into this corresponding length square plus this corresponding length square, that is 10 square plus 8 square. Now you see I am finding with respect to this axis. Okay, so this I'll have to shift it to here using the parallel axis theorem. So plus the mass multiplied by the square of the distance between them. This distance, it is 5 centimeters, so 5 square. Now due to the cylindrical portion, as such, this corresponding axis, this is a cylindrical axis. Okay, the earlier two cases it was the central diameter axis, but in this case this is a cylindrical axis. So the equation is half mr square. So minus 565.487 into 2 square divided by 2. Okay, plus now I'll have to use the parallel axis theorem to express it in terms of this z axis here. So this would be equal to the mass 565.487 into the square of the distance between them. So this will be 139200 minus 15268.15. So if I solve this, I would get 123931.85 gram centimeter square. So this is the moment of inertia with respect to the z axis. Now in this corresponding figure here, the x axis, y axis and z axis are actually the principal axis itself, since you can obtain the planes of symmetry with respect to these three axes as such. Another topic which I would like to discuss is the translation of the coordinate axis in finding the mass moment of inertia and the product of inertia. Now you see this figure here. Consider I have a reference small xyz, okay, that is at any arbitrary point, okay, and another reference x dash, y dash and z dash that is only translated here, okay, and has the same orientation as that of xyz. Okay, it may be translated, but it has the same orientation as that of xyz, and it has an origin, okay, at the center of mass. The origin of the x dash, y dash, z dash is at the center of mass. Okay, now suppose the corresponding coordinates of the origin, okay, with respect to the xyz, it is xc, yc and zc. Okay, now I'm not going into the derivation part, but if you find the mass moment of inertia with respect to the z axis as well as with respect to the z dash axis, okay, they can be related as Izz is equal to Iz plus the total mass into xc square plus yc square. Now suppose the perpendicular distance between the z-axis and the z' axis, it is d. Okay, now in this corresponding figure, suppose I am viewing this figure from top here. Okay, I am viewing this figure from top here. Then this figure will look like this approximately. Okay, you have the xy axis, okay, and the x dash y dash axis, and the z axis as well as the z dash axis is perpendicular to the screen here. Now this d is the perpendicular distance between the two axes. So from this I can get that xc square plus yc square is equal to d square. So if you substitute this value in the previous equation, you would get Izz is equal to Iz plus m into d square. So this is the equation which you had studied it as the parallel axis theorem. Okay. The same can also be represented in terms of the product of inertia. If I have the product of inertia Ixy relative to the xy reference and the product of inertia Ix dash y dash, then I can relate both these in this corresponding form. Ixy is equal to Ix dash y dash plus m into xc yc. Okay, so this equation as such is very important. Okay, you must have already studied this equation here as parallel axis theorem. You also remember this equation. Ixy is equal to Ix dash y dash plus mxc yc. Remember one thing here, the orientation of both the axes should be the same. And one more thing in this is that you should look for proper sign, okay, when applying this equation. Okay, you see here xc and yc, okay, xc and yc are measured with respect to the xy axis here, okay, with respect to the xyz axis here. So that you have to remember. So depending upon that, the corresponding value of xc and yc may either be positive or negative. Okay, now let us solve a problem here. Compute Iyy and Ixy for the right circular cylinder which has a mass of 50 kilograms and the square rod which has a mass of 10 kilograms when the two are joined together so that the rod is radial to the cylinder. Okay, so as such in this question here, the x-axis and the y-axis are shown here. We have to find the moment of inertia Iyy and Ix and the product of inertia Ixy. Now, first Iyy. Okay, so you have a cylindrical portion here as well as a solid slab here. Okay, so Iyy, first I'll consider the cylindrical part here. Now the masses of these corresponding solids are already given to you. So as such, for the cylinder, the corresponding mass is 50 kg. So the mass moment of inertia with respect to an axis, with respect to the cylindrical axis here, we know that the equation is mr square by 2. So 50 into r, you see the diameter is given as 0.25, so the radius will be 0.25 divided by 2. So this would be 0.25 divided by 2 the whole square divided by 2 plus. Now I'll have to use the parallel axis theorem in order to express the moment of inertia with respect to this axis. Okay, So this would be equal to plus 50 into. Now the distance between these two, it is 1 meter plus half of 0.25. So 50 into 1 plus 0.25 divided by 2, the whole square. Okay. Now plus. Now due to the square rod here, you see, I can find the moment of inertia with respect to an axis that is passing through the center of this rod here, and then I can use the parallel axis theorem to express in terms of this y-axis here. So that will be equal to the mass of the rod, that is given to you as 10, the corresponding length of one edge, this corresponding length, as well as this corresponding edge length. So it will be equal to 1 square plus 25 mm is the corresponding cross section. So it will be 0.025 meters, 0.025 square, whole divided by 12. Now using the parallel axis theorem, I will shift it to this corresponding edge here. So plus the mass multiplied by square of the distance between these two, that will be equal to 0.5 square. So if I solve this, I would get 63.672 plus 3.334, which will be equal to 67.01 kilogram meter square. I had expressed all the corresponding values in meters. Now next I have to find the value of Ixy, the product of inertia. Now for this cylinder here, principal axis, due to that symmetry, this will be, say I call it x1, so this will be x1 and this will be y1. Okay, and similarly for this rod here, I can obtain the since there is a plane of symmetry here, I can obtain the principal axis for this rod here. So this, say this is x2 and this is y2 here. So as such, I can obtain the product of inertia of both the cylinder as well as the rod with respect to this axis shown here. So Ixy, the product of inertia m, will be equal to. Now you must remember one thing in mind. For this corresponding cylinder here, the product of inertia Ix1 y1, Ix1 y1 will be 0 here. Because this is the principal axis. X1 y1 are both principal axis. So as such, Ix1 y1 will be equal to 0. Similarly, for this rod here, okay, since this both x2 y2 are the principal axis, Ix2 y2 will be 0 for this rod here also. Now I should be able to express this in terms of the x and y coordinate reference here. So as such, I should use the transformation of the coordinate equation in order to express it in terms of x and y. So this as such will be equal to, for the cylinder, Ix1 y1 plus m into xc1 yc1 plus Ix2 y2 plus this, say if we call this was m1, m2 into xc2 yc2. So this will be equal to 0 plus 50 into xc1 yc1. Now here x1 and y1 is the reference frame. It is attached to the mass center here. Okay, so with respect to this reference frame here, xc1 will be negative here. Okay, this corresponding distance is xc1 here. Okay, and yc1 is this corresponding distance. Okay, so as such 50 into, now xc1, it is towards the left of the xy axis, so as such this will be minus 1.125, and yc1, it is in the upward direction, it is positive here, so that value will be equal to half of 0.5 here. Okay, so 0.5 divided by 2 plus, now ix2 y2, the product of inertia ix2 y2 will be equal to 0 plus m2, the mass, it is 10 kg, into xc2 y2. Now xc2 as such is this distance. Okay, since it is towards left, it is half of this 1 meter, that is minus 0.5 meter multiplied by, now this x is at the bottom of this rod here. Okay, while this x2 y2 is at the center of this section here. Okay, so as such the distance between these two, okay, since this is a 25 mm rod, the distance will be half of this, so 25 mm, it will be 0.025 divided by 2. So this will be equal to minus 14.063 minus 0.0625. So as such you will get this as minus 14.125 kilogram meter square. Okay. So this is the product of inertia for this corresponding solid. So with this we come to the end of the questions that is related to the mass moment of inertia. In the next class we shall start with the problems of pure rotation followed by the general motion. So thank you all.